Okay, welcome you all for the today classes. In the previous classes, we were discussed about the application of Bernoulli equation to the devices, some devices. So those are the venturimeter. Already we completed the application of Bernoulli equation to the venturimeter. Okay, so now and the today classes we are going with another devices, that is the orifice meter. Okay, so an orifice is the small aperture through which the fluid passes. Okay, the thickness of an orifice in the direction of flow is very small in comparison to its other dimensions. Okay, so you can say that if you take one uh, circular plate, so inside in that circular plate we can make only one small hole, so that will become our orifice meter. Okay, if you take one circular plate, inside that center of that circular plate we can make the one hole, then it will become our orifice meter. So what is why where we can use this orifice meter? So again we are used this orifice meter to find out the discharge or flow rate through the pipe. The function is same as that of the venturimeter. Okay, this is also a flow measuring devices or discharge measuring devices. Okay, if a tank containing a liquid has a hole made on one on the side or base through which the liquid flows, then such a hole may be termed as an orifice meter. So already I told you, if you are taken one plate, circular plate, so center of the circular plate if you are make one hole, then it become our orifice meter, then it becomes our orifice meter. Here he has taken one tank, so inside the bottom of that tank we will make one hole, then that will become our orifice meter. The term is become orifice. The rate of flow uh, of the liquid through such an orifice at a given time will depend partly on the shape, size and form of the orifice meter. That thickness, it all depends upon their size, hole size and thickness of that plate. So it depends upon those parameters. Okay, an orifice usually has a sharp edge so that there is a minimum contact with the fluid. Okay, if you are making one hole, so that will form the sharp edges, that hole sharp edges. Okay, fluid, and consequently minimum frictional resistance at the side of the orifice. So the contact between the fluid and that hole surfaces is minimum, so obviously it will reduces the frictional resistance. If the sharp edge is not provided, the flow depends on the thickness of the orifice and the roughness of its boundary surfaces too. Okay, if the hole, whatever the hole is there, that edges is not so much sharp, so it then the floor, it depends upon the thickness, how much thick is that plate, hole of that plate, and the of the orifice, and the roughness, how it will get roughed. Okay, how will get finished. So it depends upon the flow rate, is depends upon those two parameter. If it is not sharp edge, it is not having the sharp edges. Okay, see here next one. So again, orifice meter, it is a device used for measuring the rate of flow through the pipe. So similar function as we discussed in the venturimeter, and it is the cheaper devices as compared to the venturimeter, because it is having only one sections, that is the third section. You can say that third section, only one hole is there, so it will become cheaper as compared to the venturimeter. The basic principle on which orifice meter works is same as that of the venturimeter, but the principle of working is same as that of the venturimeter, but the construction is simple here, and it is cheaper than the venturimeter, but the working principle is as same as that of the venturi meter. Okay, it consists of a circular plate with a circular opening at the center. This circular openings is called as a orifice. Okay, and the diameter of the orifice is generally varies from 0.4 to 0.8 times the pipe diameter. So if suppose if the pipe diameter is 10 centimeter, if that pipe diameter is 10 centimeter, and the if it is having the orifice which is connected to the that pipe, then that orifice is 0.8 into the diameter of the pipe, or 0.8 into into diameter of the pipe, or 0.4 into diameter of that pipe, or the values between 0.4 to 0.8. You can take any value between the 0.42 and 0.8, and that value is multiplied with the diameter of that pipe which is connected to the orifice meter, will gives us the hole which is present in the circular pipe, a circular plate. So that will makes the orifice to us. Okay, so this is the very important conditions here. This is very important conditions to design the orifice meter. Okay, it is also flow measuring devices, and it is cheaper than the venturi meter. Okay, the principle of working is same as that of the venturi meter. Okay, that hole, orifice hole, is having 0.4 into 0.8 into the multiplication of the pipe diameter, the pipe which is connected to that orifice plate. Okay, so that will help us to design the orifice plate. Okay, so now here if you see here this figure, so this figure will shows the uh, orifice meter plate. So this is the direction of flow, and this is the pipe here. Okay, this is the pipe. Inside that pipe the fluid is flowing. Okay, this is the orifice plate. This whatever the black line is that, that is the orifice plate. So there is one circular plate. Inside that circular plate we are having one hole. So the diameter of this hole, it depends upon the 0.8 or 0.4 to 0.8 into multiplication of this diameter of pipe. So how to decide this hole diameter? So that multiplied 0.4 to 0.8 any value with the diameter of this pipe, we will give the diameter of this orifice plate hole. Okay, so again here it is the distance is here 2d, and here it is the d by 2. That fixing of this differential manometer distances at this positions, we have to fix that one, and it is fixed with the 2d. That d is the diameter of the pipe. 2 into d, if you multiply that diameter pipe, so at that point we are connecting this U2 manometer point, one point, and here in this right side d by 2, whatever the distance is that d by 2, that point we are going to connect this differential manometer one end. Okay, this is the manometer. Okay, we will get the differences here, differences here, pressure differences at this point and the pressure differences at this point, we will get it. This is will shows the x value here. Okay, this is the schematic representation of orifice meter. Okay, now expressions, we have to derive that expressions as similar to the venturi meter. Okay, so here let d1 diameter at section 11, p1 same, p1 pressure at section 11, p1 velocity at section 11, p1 area of cross sectional at 11. Let the same things d2, p2, v2 and a2 be the corresponding values at section 22. Suppose if you are taken here, it is the section 11 and section 22. So whatever the parameter we considered at section 11 is same as that of the parameter we are considering at section 22. What are the parameter? Diameter, pressure, velocity, area. So the same corresponding values at section 22. Okay, so now we can applying the Bernoulli equation between the 11 and 22. We have the same procedure for the orifice meter also. Okay, see here, this is our Bernoulli equations. We can apply that Bernoulli equation to the two sections 11 and 22. So we will get that p1 by rho g plus v1 square by 2g plus z1 is equal to p2 by rho g plus v2 square by 2g plus z1. Okay, again the procedure to derive that q discharge is same as that of the venturi meter here. Okay, since pipe is horizontal, again z1 is equal to z2, then we will left with p1 by rho g plus v1 square by 2g is equal to p2 by rho g plus v2 square by 2z. Okay, so again we have to simplify this. P1 minus P2 by rho g is equal to Vt square minus V1 square divided by 2g, or H is equal to Vt square minus V1 square by 2g, or 2gh is equal to, just we have to take this term, 2gh is equal to V1 square minus Vt square. Okay, simplified. V2 is equal to root of just we need this term V2 is equal to what, if we have taken this side, then it becomes 2gh plus V1 square. This is equation number 1. Okay, so we get this V2. Now section 2 is at the vena contracta, and A2 is representing the area at that vena contracta. So that if the area A0 is the area of the orifice, then we have vena contracta, that is CC is equal to A2, that area which is representing the vena contracta divided by the area of orifice meter, that is A2 by A1, where CC is the coefficient of contraction. This CC is equal to coefficient of contraction. Okay, so now A2 is equal to, so this A2 is equal to CC into A0, see A2, A0 into CC. Okay, coefficient of contraction. So from continuity equations we have A1 V1 is equal to A1 V1 is equal to A2 V2. So this is equation number 2. Or V1 is equal to, this V1 is equal to what, A2 by V2, A2 V2 by A1, which is into A2 V2 divided by A1. Okay, again V2 is equal to A0. Okay, because this A2 is we know that A2 is equal to A0 CC, that A0 CC, this A2 is placed with here, substitute with this value A0 CC divided by A1 into V2, A1 into V2. Okay, so here equation number 2, substituting the value of V1 in equation 1 we get, so already we know the equation here 1, in the equation V2, so just we have to substitute that value. V2 is equal to what, root of 2gh plus, so whatever this value is there V1, just we have to substitute here, then it becomes A0 square CC square V2 square by A1 square, this here. So this value, in this value V1 value we have to substitute from this equations. Okay, so that it becomes V2 is equal to root of 2gh plus A0 square CC square V2 square divided by A1 square, then V2 is equal to root of 2gh divided by, just we have to take divided by 1 minus root of A0 by A0 by A1 whole raised to square into CC square. So substituting the value of V2 in the equation Q is equal to A2 V2, that is discharge Q is equal to A2 V2. So already we know the value of V2 here, just we have to substitute that value in the Q equation. So we will get that Q is equal to A2 is as it is here. Okay, so that V2 is becomes what, this root of CC root of 2gh divided by root of 1 minus A1 AC square by A1 square into CC square. This is equation number 4. Okay, so now above equations can be simplified by using CC is equal to CD root of 1 minus A1 A0 by A1 square divided by root of 1 minus A0 by A1 square into CC square, or you can say that CD is equal to CC, just simplification is there, nothing. Okay, root of 1 minus A0 by A1 square CC square divided by root of 1 minus A0 by A1 square. Okay, and substituting the value of CC in equation number 4, so that you have to substitute that value, so this CC value in the equation number 4, so we will get that Q actual is equal to A0 into CD, A0 into CD, this equations. Okay, root of 1 A0 by A square CC square divided by root of 1 minus A0 by A1 square into, so into you have to substitute this value, root of 2gh divided by root of 1 minus A0 square by A1 square into CC square. So again we have to simplify this term and this term will get cancelled, we left with CD into A1 A2 CD into A1 A2 root of 2gh divided by root of A1 square minus A0 square. Okay, where CD is the coefficient of discharge for the orifice meter, so this is the Q actual term, Q actual. Okay, if you remove this CD, then it becomes a Q theoretical. The equation is and derivation procedure is same, to same in both the conditions, venturi meter as well as orifice meter. So with this we completed today classes, and next classes we will move on to the next application. Thank you.